Okay. So for the last half of the semester, we're going to concentrate on hazards that are tied to the Earth itself, geological hazards. Up till now, Dr. Larrick has been talking to you about atmospheric hazards, and now we're going to shift and talk about geologic hazards. And most of the geologic hazards that we'll discuss in this class, earthquakes, volcanoes, tsunamis, can all be tied to the way that the Earth works. And the way the Earth works is that it has a very active surface where various crustal plates move around and interact with one another, causing these volcanoes and earthquakes and tsunamis. So we're going to spend today and part of next class talking about plate tectonics, how it works, and then how it influences the various hazards that we talk about. So what we'll do first is talk about 4 or 5 concepts that you'll need to know and understand in order to have a better idea of how plate tectonics works. We'll talk a little about the history and then a little about the idea itself. Plate tectonics is kind of a unifying theory for Earth scientists, but it's only been around as an idea for about 100 years. And when it first came out, it wasn't well accepted by scientists. It was actually proposed by a German climatologist, not even a geologist. And it had some problems in its early days, but as scientists learned more and re-examined this idea, they found that a lot of aspects of it really made sense. And then there was some new information that came out in the 1950s that really suggested that this is how the Earth works and how it affects various hazards like volcanoes, earthquakes, landslides, and tsunamis. So let's go through the background topics first. If you have any questions, I really like to be interrupted. If you have questions, just shoot your hand up. I'd rather take some time and answer your questions than just plow mindlessly through the notes. So anytime you have a question, just either throw your hand up or shout it out. Okay, so the first topic that we have is heat and pressure. And it's pretty easy. All I really want you to remember from this topic is that as heat increases on anything, the atoms in that system will vibrate more rapidly. So when things are really cold, atoms vibrate really slow. As you crank up the heat, they vibrate faster and faster and faster. And generally what happens when atoms vibrate faster, they take up more space. And what that results in is that material being a little less dense because it's taking up more space and you have the same amount of material. That lowers the density of the material. A good example of that would be our air. If you heat up air, the atoms that are in the air vibrate more, take up more space, become less dense, and for that reason, warm air rises. So if you increase the heat, you increase atomic vibration. So that's one of the concepts I want you to keep in mind. The second is pressure. Now in geology, pressure usually comes by burying things deep in the earth, okay? And as you increase the pressure, you increase the way that atoms pack together. Atoms pack together more closely when you increase the pressure. And like I said a minute ago, in geology, we tend to get increases in pressure when we go down deeper into the earth. And I use this as an example all the time. If I took you into my backyard and dug a hole that's maybe 3 feet deep, threw you in it, and then buried you with the dirt, you'd have about 3 feet of dirt on top of you, right? And you would feel some pressure, and that pressure is from the Earth's gravity pulling that overlying dirt on top of you down on top of you. Now, if I dug another hole that was 20 feet deep, threw you in that and buried you, you'd feel more pressure, right? And as you go deep, deep, deep into the earth, there's more and more overlying material that's being pulled down by gravity and that's what creates the pressure. And when you squish things under pressure, it forces all the atoms to pack together a little more closely. I just talked about gravity. It's something all of you know about, right? Everybody knows about gravity, but maybe you don't know as much as you thought about gravity, okay? If you ask most human beings, what is gravity? They're going to say, well, it's the force or it's the attraction that keeps us on Earth, right? It's actually more than that. And in geology, it's important that we understand that it's a little more than that. Gravity exists between any object that has mass. And gravity is the force of attraction between things that have mass. So, do you have mass? Does the person sitting in front of you have mass? You are actually gravitationally attracted to every person in this room. You're attracted to me whether you want to be or not, because I have mass and you have mass. You're attracted to the person closest to you. Does the ceiling have mass? Sure, you're attracted to the ceiling. You're attracted to the floor. You're attracted to me. You're attracted to your fellow classmates. Anything in this room that has mass, you are attracted to. Okay, it's not just the Earth. But you're stuck to the Earth, right? You're attracted to me, but you're not all sort of physically coming towards me, right? You're sitting in your seat, the Earth is pulling you down. That's because of all the things that have mass around you. The Earth has the most mass, okay? So it has the most gravity. So you feel its gravitational attraction more than any of these other gravitational attractions that are out here. But I will ask you this, what has more mass, the Earth or the sun? The sun has a lot more mass, right? So why aren't you all zooming off towards the sun? It's because there's a distance component to it as well. So the way gravity actually works is that it's the force of attraction between things that have mass. So the more massive the two bodies, the more the gravity is going to exist between those two objects, the greater the gravity. But it's also tempered by the fact that the farther these two bodies are apart, the less the gravitational attraction will be. So the most gravity will be something big that's close to you. You can have massive things out in the solar system, but they're so far away that their gravitational attraction is just muted to the point where you really don't feel it. Okay, another similar but different concept is magnetism. Magnetism has some similarities to gravity, but also some important differences as well. Magnetism is the force of attraction between things that have a charge or things that have poles. Okay, so let's pretend that this right here is a magnet, okay? If I let go of it, what's going to happen to it? It's going to fall, right? Why is it falling? Because of gravity, but it's a magnet, right? I just told you it was a magnet. But magnets have mass, right? So magnets are kind of unique in the fact that they're going to have two kinds of forces connected to them. They have mass, so they feel gravity, and they have some gravity themselves, but they're also influenced by surrounding charges and poles. So let's say the ceiling was also a magnet, okay? Now, I have a magnet in my hand, ceiling's a magnet. What are the possibilities for if I let this magnet go, if the ceiling is a magnet? What could happen? It could fall, right? Because in that case, gravity pulling down would be greater than the magnetic force pulling it up, right? Or let's say the ceiling was a really strong magnet, right? If I let go, if the magnetic pull of the ceiling was greater than the gravitational pull on the mass of the magnet, it might go up. What if the magnetic pull up was equal to the gravitational pull down? It would probably levitate. Yeah, it could just sort of sit here. It would be hard to do, but theoretically that would be possible. So gravity is the force of attraction between things that have mass. Magnetism is the force of attraction between things that have a charge or poles. And we're going to spend a fair bit of time on both gravity and magnetism because both of those concepts really influence plate tectonics. Not only in how it works, but how we actually discovered that plate tectonics is a real thing. So similar to magnetism, or similar to gravity, magnetism is greater when the charges are greater. Just like with gravity, gravity is greater when the masses are bigger. And just like gravity, magnetism also has a distance component. The farther apart the two poles or the two charges, the smaller the attraction, or in some cases repulsion, is going to be. Now, most of you probably know that the Earth behaves like a large magnet. If you've ever taken a compass out, right? What do compass needles do? They point north because they're magnetic, and the Earth has a magnetic pole at both the north and the south. So not only will magnets that you have in your hand point north, but on Earth, we have volcanoes that produce lava flows. And a lot of lava flows have a little mineral in the lava called magnetite. It's a little needle-shaped mineral that's magnetic. It's a lot like the needle in your handheld compass. Okay, and there's thousands of these things in lava flows. And when a nice fluid lava flow comes out on the Earth's surface, it has all of these little magnetic needles inside of it. And they feel the Earth's magnetic field. And they will actually wiggle around and try to align and point north, just like your compass needle would. And then the lava flow cools, hardens, and locks those magnetic needles in place, pointing towards the pole. It's kind of neat. But for a long time, it really wasn't considered to be anything too exceptional. Yeah, it was kind of cool. Lava flows have little magnetic needles, and these magnetic needles point north. But somebody looked at lava flows that were a bit older, and what they noticed was that a lot of those needles in older lava flows pointed south. And then older ones yet pointed north, and older ones than that pointed south. So it looked like over time the Earth's magnetic field switched from north to south, which was kind of interesting and something we're going to come back to here in a second. So the Earth is a big magnet. It's got a north pole, it has a south pole, and it's a powerful magnet. Yeah, question?
How would you know which way they're pointing? North and south are the same direction.
Okay, so she asked, how would you know which direction it's pointing? You know, because north and south are 180 degrees. You know, if you flip them around, they kind of look, because you can actually tell the polarity on the little needles, just like you can on your compass as well. One side will always point to the north. So let's just say the positive side always points to the north. Well, in the older ones, that same positive side actually pointed to the south. So you can look at the polarity on the little magnetic needles, and they actually switch in the older rocks. So since this Earth is a big magnet, and remember, magnets attract charged particles, That's what magnets do. They attract poles and charged particles. What the Earth actually does sitting out there in space is that it can attract charged particles that exist out in space. And our sun, when it goes through its nuclear fusion cycle to create heat, it also creates a lot of charged particles that stream out in all directions from the sun. And this is called the solar wind. So it's basically just material from the sun, atoms from the sun that have charges, and they spread out in all directions, and they go whizzing out through space. Now, when they get close to the Earth, though, because they are charged, and because the Earth acts like a magnet, there's going to be an attraction between the two. And the Earth kind of surrounds itself with these charged particles from the sun. And that layer of charged particles is something called the magnetosphere. Okay? So this layer of charged particles, or the magnetosphere, is a pretty big system. It extends out past the moon. So even the astronauts that traveled to the moon were still inside our magnetosphere. This magnetosphere is really important for you, for our technology. It acts as a protective shield from space radiation. There's lots of nasty radiation out in space. There's gamma rays, there's X-rays, there's cosmic rays. All of that radiation is potentially damaging not only to life forms like you and me, but one thing that we've done in the last 50 years is we spent a lot of time, a lot of money putting satellites up into space. And satellites do a lot of work for us. It's a big factor in communications. Commerce is done through satellites, banking done through satellites, GPS system done through satellites. Just about everything today relies on GPS rather than compass and maps in order to navigate. But this space radiation is really harmful, like I said, for not only humans, but for satellites as well. So we need this magnetosphere to protect us and our technology from all this nasty stuff out in space. Now, the magnetosphere is not something you can generally see. On occasion, though, if you get up near the poles, anybody seen the northern lights? Or maybe the southern lights if you've been in Antarctica? Yeah, that's actually those charged particles being attracted to the Earth's magnetic poles, dancing and interacting with one another. So the Aurora Borealis and Aurora Australis, I believe, both are from those charged particles attracted to the Earth's magnetic field, interacting with one another, creating this pretty amazing light show. So the Earth behaves like a magnet. Compass needles feel that magnetic pole. Little magnetic minerals and lava flows feel that magnetic pole. And like I mentioned earlier, if you take your compass out today, one end of it is going to point north, and the other end will point south. And little magnetic needles and lava flows are going to do exactly the same. But in the 1950s, some geologists discovered that some older lava flows had what we call a reverse polarity. They did just the opposite. The pole that normally pointed to the north in those rocks, and those magnetic minerals in those rocks, actually pointed the opposite direction, south. And then they looked at slightly older rocks than that, and they pointed north. And older ones yet pointed south. And this has apparently happened throughout a lot of geologic history. And what that means is that our magnetic field reverses from time to time. That doesn't mean that the Earth physically flips over. It just means that the North Pole and the South Pole switch their magnetic polarities. The north end, rather than being a positive feature, becomes a negative feature, and vice versa. So what? What does this really matter? Big deal. Lava flow minerals flip-flop from time to time. Well, it's interesting from a couple standpoints. One, it tells us something about how the Earth behaves. And two, it brings up a potential hazard for us as humans. Now, as you look back at the rocks, what they were able to determine is that the Earth has actually flipped its magnetic poles pretty frequently, 24 times in the last 4 million years. Okay, that's the same as 6 reversals every million years, or on average, 1 reversal every 170 to 180,000 years. Geologically, that's pretty quick. What do you guys want to know? Yeah.
Would it have an effect on us if it happened?
Would it have an effect on us if it happened? That's a great question. Now, in the lab, we can play with magnets all the time, right? And that's what scientists do. It's like, well, we can't make the Earth do anything. It's big and powerful. It's going to do what it does. But maybe we can learn something by taking magnets into the lab and playing around with them. And that's exactly what we did. And what we found out is that when you reverse the polarity on a magnet, as that's happening, while those poles are shifting, the magnetic field drops to 0. Do you think that's good? Because if the magnetic field drops to 0, what happens to our protective magnetosphere? It's not there, right? So it allows lots of radiation to come through. So it's potentially bad for humans. Now, if this happens really quick, then only a little radiation gets in and, we'll be okay. And humans have been on planet Earth for about 2 million years, okay? We've had probably 12 of these reversals since humans popped up in the fossil record. Did we survive? We did. Now, that doesn't mean that all reversals happen the same way. Maybe some go really quick, maybe some take a long time. So we don't know if future reversals are going to happen as quickly as the past. Maybe they'll go longer. We just don't know because we haven't had one during sort of modern scientific times. Okay? So, yeah, there's concern because when magnetic poles flip-flop, the strength drops to 0, which means our magnetosphere can go away and lots of radiation come in. Radiation is bad for living organisms. It's really bad for technology. What else do you want to know? What's that? What causes them to switch? We don't know. We really don't know. We're not even totally sure why the Earth has a magnetic field. We think it's because the Earth has a liquid outer metal core that moves around. We know that you can make magnetic fields by moving charged particles. And in the outer core with all this metal is lots of charged particles. And if it's liquid, then it can move around. So we think it has something to do with what goes on in the outer core. Problem is, we don't know that much about the outer core. We've never been able to drill down. So we're doing lab simulations like we did with magnets to try to get some idea how it works. But as of right now, we're just not sure, first of all, what causes the magnetic field, and then what causes it to flip-flop. And you had another question?
How do you do the lab?
They take liquid metal and put it in a big spherical drum and rotate it and see what kind of magnetic fields it generates. So we're trying to mimic what goes on inside the Earth. We don't know if we're doing a good job of it now. It's kind of a new field. Any other questions you have? One that you should have, maybe you thought about it, maybe you didn't, is how long since the last one? How long has it been? As it turns out, it's been pretty long. So if you look at the average over the last 4 million years, we get one of these reversals on average every 150 to 200,000 years. Now, on a human time scale, that's really long. On a geologic time scale, that's really fast. As it turns out, it's been about 700,000 years since the last one. What does that mean? It means we're potentially way overdue for one of these, right? And as it turns out, over the last 20 or 30 years, the Earth's magnetic field has been acting really strange. It's been weakening. It's about 30% weaker today than it was just 40 years ago. And it's moving. The Earth's magnetic pole is sort of up around the North Pole, but it moves around a little bit. For a while, it was over by Hudson's Bay, Canada, and it would migrate a little bit. But in the last 15 years, it's just decided to take a stroll. It's way over by Siberia now. And we don't know why it's doing that. We don't know why it's getting weaker. We don't know why it's wandering the way it is. We don't know if this is just the way it behaves naturally, or are we gearing up for one of these magnetic reversals? We just don't know at this point. But there's certainly a lot of attention being paid to it because it could potentially affect us as life forms, and it could certainly affect our technology. So kind of the bottom line in all this is that the Earth is a big magnet. For time to time, for reasons we still don't understand, it flips in polarity. These are called magnetic reversals. During a reversal, it's likely that the strength of the magnetic field will drop to zero. During that time where there isn't a good, strong magnetic field, we will lack the protection from all of those charged particles in space that make up our magnetosphere. That will increase the amount of space radiation that can enter Earth, bombard your soft tissues. But even more importantly, it would completely disrupt global communications, banking, commerce. You would probably not be able to withdraw money from the bank. You wouldn't be able to use your ATM cards. You probably wouldn't be able to make a phone call. You think of how dependent our life has become on technology. The internet would shut down. GPS would shut down. Air traffic would therefore have to shut down. So this could be a real mess. Even if it went on for just a few days, it would likely be a mess. Now, do we have one that's imminent? I have no idea. It is concerning that the strength of the magnetic field has been dropping. It's been moving around. But we just don't know if that's just a natural waxing and waning of the magnetic field or not. Yeah, question.
How long will it take to switch?
Oh, so she asked, how long does it take to switch? We covered that a little bit, but the thing is that what we don't know is that whether future reversals will be as fast as past ones, and we're not totally sure how long the past ones have taken, although I did read a study about 3 or 4 years ago. They were looking, geologists were looking at one lava flow in Oregon, okay? So the lava flow came out, it's all molten, all those little magnetic needles lined up to the north, but as the lava flow was cooling, there was apparently a reversal. So what happened was the magnetic needles that pointed north and then were trapped in place by the cooling lava, the lava became solid rock, they still pointed north, but inside the lava flow where it stayed hot a little longer and molten a little longer, they actually turned and pointed south after the reversal. And so you had a lava flow where at the very top all the magnetic needles were pointing north, and in the middle where it stayed molten longer, they're all pointing south. And you can do little models of cooling of lava flows to get an idea of how long does it take for a lava flow to cool from the top to the middle. And this particular lava flow took about 4 days. So it looked like that reversal happened in about 4 days. So that's not enough radiation to kill you or maim you or make you have mutant kids or any of that stuff. Probably not enough to give you cancer. 4 days, though, without banking, internet, communications, it's not the end of the world. But I've seen you guys when, you can't charge your cell phones and the panic that takes place if you can't get on your email or any of that stuff. And this goes on for days and days. Yeah, people could completely freak out over it. We're not going to have massive death and destruction if it only goes on a few days. But what if it went on a month? What if it went on 6 months? What if it went on 3 years? Then you'd start to be concerned. So we don't know if all of them take the same length of time. It looks like the ones in the past were probably pretty quick. I mean, we're still here, right? It wasn't long enough to cause an extinction. But we don't know if future ones will be longer, shorter, or the same length of time. Yeah? Do the ones in the lab vary in time? Yes, they do. It depends on how they're being spun. But we don't know if our lab experiments are really mimicking nature all that well because we don't have enough data from nature to be able to reflect back on our lab experiments and say, yeah, you did them right or not. So there's a lot about this we simply don't know. But we're going to come back to this because this switching of poles is actually some of the evidence for plate tectonics. Okay, one of the last concepts that we'll talk about here is buoyancy. And this one, you might not think, it's like, what would this have to do with plate tectonics? It actually has a lot to do with plate tectonics. Buoyancy is the process where less dense materials rise to the top of the system and more dense materials sink. You guys have probably seen this with oil and water, right? When you pour oil into water, what happens to the oil? Floats, right? And it floats because it's less dense than the water. So you're used to that with liquids. It works with air as well. Warm air rises, cold air sinks. That's the origin of our wind. Believe it or not, it works with solids, with rocks as well. And it works with plate tectonics. And I will show you here. So out in the ocean, if you look at the rocks at the bottom of the ocean, they're really different than the rocks that we have here on the continents. They're denser. They're about 25 to 30% denser than the average rock that we have here on the continent. Okay? So you guys kind of know how heavy rocks are, right? Now those are rocks you're picking up here on the continent. If you were to pick up the same size rock from the ocean floor, it'd be 20 to 30% heavier. Okay, it's denser. Now what happens when you have, let's say, a dense rock or a dense plate of crust, and we'll get into these terms here in a little bit, that collides with a less dense piece of crust, is that the more dense piece tends to slip beneath the less dense piece. So we have dense ocean rock, we have less dense continental rock. So when ocean rock and continental rock collide, the ocean rock slips beneath the continent and forms these cool little descending zones called subduction zones. Okay, so you get a subduction zone whenever you have a dense plate colliding with a less dense plate. The more dense plate will always take the dive and subduct beneath the less dense plate. Okay? Question for you. What's the tallest mountain range on Earth? Where are the tallest mountains on planet Earth found? The Himalayas, okay? Yeah, if you go there, Mount Everest is there, 29,000 feet. Lots of peaks over 25,000 feet. Tallest mountain range on Earth. Question I have for you is, why would you get mountains that tall just in that part of planet Earth? Well, it has to do with this density thing I was just talking about. So here's India. The Indian subcontinent you see here is continental, okay? It's continental rock. It's smashing into the Eurasian plate, which is continental rock. They're both the same kind of rock. Is there any difference in density? No, so when they collide together, there's no tendency for one plate to dip beneath the other. Neither one wants to take the dive. They're both the same density. So what they do is they just sort of plow into one another and just buckle, and the crust gets really, really super thick right here because neither one wants to subduct because they're the same density. So instead of one slipping beneath, they just sort of buckle in place. The Earth's crust gets really thick, and on the top end of it is this really tall mountain range. So by far the tallest mountains on Earth, and it's because you have two plates with the same density colliding into one another and neither one wanting to give way. Okay, before we move on and talk about plate tectonics, we need sort of a working idea of what our Earth looks like on the inside. Now, what's kind of interesting is we've never been inside the Earth, really. The deepest mines in the world are only about 2 miles deep. The deepest mine in North America is just up in South Dakota, the Homestake Gold Mine. I used to live right by it. I actually went to the bottom of that mine. It's 10,000 feet deep. You get down there by elevator. It takes about 20 minutes to get to the bottom by elevator. You just get on this thing and you just take a ride for 20 minutes. It's the weirdest thing. But as you go down, it gets hotter and hotter and hotter. And by the time you get down 2 miles into the Earth, temperature is somewhere around 125, 26 degrees. There's no air moving. It's miserable. It's one of the worst places I've ever been. I don't know how the miners work in that. And in fact, that's why that mine closed up. It's not because they ran out of gold. It's because it was just too hot to work. I mean, they could have pumped air conditioning down, but that cost so much money that it wouldn't have been worth extracting the gold because you're spending so much to get it out. That's only 2 miles deep. It is almost 4,000 miles to the center of the Earth. We haven't even hardly explored any of the Earth, from that perspective. We've only been down a couple miles. The deepest drill hole, just a few more miles deep than that. We've never even drilled to the next layer down from what we're standing on, the mantle. We only have direct evidence about the Earth's crust itself. So everything I'm going to show you here is what we've learned from indirect evidence. But what we think is happening in the Earth is at the very center is a core of solid nickel and iron. This is like the world's biggest ball bearing, but it's really hot. It's under tremendous pressure. And just outside of that is this zone that we've been mentioning a little bit, which is the outer core. It's the same material as the inner core. The only difference is that instead of being solid, it's liquid. So it can move around. And it's this moving liquid metal that probably gives rise to our magnetic field. Now, even though this is liquid, this is not where volcanoes get their magma from, okay? This is liquid metal, okay? If you go to volcanoes don't spew metal out onto the ground. They spew molten rock. So magma that we have in volcanoes, and when we get to the volcano chapter here in a couple weeks, it's not coming from this zone, okay? This stuff is just too heavy and dense to rise through the overlying rock. So it stays down there. If it really did get up to the surface, we would see liquid metal lava flows, which would be super cool, but they just don't happen, okay? So this is liquid nickel and iron, super dense. It's going to stay in the core and not rise up to the surface. But we're pretty sure it's down there. Why are we pretty sure it's down there? It actually has to do with earthquake waves. So when we get to earthquakes, we'll talk about this a little bit. Some earthquake waves cannot penetrate through liquids. And if you get a large earthquake on one side of the earth, these earthquake waves won't make it to the other side of the earth because there's something molten inside that's dampening them out. And I will show you some diagrams of this when we get to that chapter. So just sort of keep that in mind. Okay, above the outer core and directly beneath the rocks we're standing on, something called the mantle. The mantle by volume is the biggest zone in the earth. It's made of dense rock. It's about 50% denser than the rock that you might pick up here on the continents. It's about 25% denser than rocks that you find in the ocean. It's got really cool minerals like garnets, olivine. We have never been to the mantle, okay? We've never drilled there. We've never dug a mine there. Actually, I have a piece of it in my office, though. I have a piece of the mantle in my office. And I didn't dig down to get it. Nobody drilled down to get it. It was actually brought up by a volcano. The mantle is where magma is produced for our volcanoes. So a lot of times what will happen is, as magma is rising from the mantle, it'll actually pluck off pieces of the solid mantle and drag it up to the Earth's surface. So even though we've never been physically to the mantle, volcanoes are nice and bring pieces of it up to the surface for us to look at. So we do have a little bit of direct evidence about what the mantle is. And then finally we have the Earth's crust. That's where we are. And basically we have two kinds of crust. We have the ocean crust, which is pretty dense. It's also pretty thin. It's only about 7 kilometers thick. And for you true Americans who refuse to learn your metric system, that's just a little over 4 miles thick, okay? So that's pretty thin. You know, if you wanted to drill to the mantle, this would be where you want to do it. That's where the thinnest rock is. Problem is you got this big water layer over the top of it, and ocean water moves, so it makes drilling really difficult. So you have thin, dense crust in the ocean, about 4 miles thick. Here on the continents, the crust is a bit thicker, about 50 kilometers thick, or 31 miles. And remember, we've only been able to really drill down just a couple of miles, and our deepest wells, or our deepest mines, are only about 2 miles deep. So the Earth is a really big place. Big place with lots of resources. People worry that with increasing population, we're going to run out of some materials from the Earth. We're really not going to run out anytime soon, but what we are running out of is our ability to go get them. We just don't have the technology to go down to the great depths where we might be able to find this stuff. There's lots of gold, silver, lead, platinum, copper at depths much more than 2 miles in the Earth's crust. It's just too hot, too much pressure, and we lack the technology to go down and extract it cheaply. Okay, so that's what we think the Earth is like on the inside. Here's a little diagram that sort of shows that. So it's 63,000 plus kilometers from the surface to the center. That's about the same distance as traveling from LA to Boston. So that's how far it is to the center of the Earth. It's hot down there. The center of the Earth is about the same temperature as the surface of the sun. Now, stuff that hot, what do I say about atomic movement with heat? What do atoms want to do when they're that hot? They want to move, right? They want to move all over. But it's a solid. A solid means that the atoms aren't moving relative to one another. The reason it's a solid, even though there's so much vibration, is that there's so much pressure. It's like a clown car. You know, if you jam enough people into a car, you just can't move, right? You can wiggle all you want, but you can't move relative to your neighbor. That's kind of what's going on in the inner core. All these atoms, they really want to move, but they're being squished so much that they really can't. As you move out a little bit, you get a little less pressure. It's still really hot. A little less pressure at some point means this material can start moving. And that's why you have this liquid outer core. And again, we've never been there. We've never drilled down there. Then you have the mantle. We've never drilled there either. It's the biggest zone in the Earth by volume. And then this very tiny black line on this diagram, you can see there is a inset up above there, and it shows that that's the crust. Really thin by the oceans, just 4 miles. 1/1000th of the distance from the surface to the inside. And it's about 30 miles thick here on the continents. So that is probably the best idea that we have as geologists right now for what the Earth looks like on the inside. Even though we haven't been there, we have some indirect evidence that tells us that this is probably what's going on down there. There's certainly a lot more to learn. And what we'll spend the rest of the time talking about is how the very upper zone, the Earth's crust, interacts to give us not only the features that we have here on the surface of the Earth, but also some of the hazards. Okay, I mentioned before, where does magma for volcanoes come from? It actually comes from the upper mantle. Usually where you get these subduction zones, where you get this ocean crust that's slipping beneath the continental crust, as it descends, there's some chemical reactions that take place that allow melting to occur. When that material melts, it's a little less dense than its surrounding, and it wants to rise up to the surface, okay? So magma is created here in the upper mantle, not way down deep in the core. So pretty close to the Earth's surface. Maybe down 60, 70, 80 miles, which might sound like a lot, but when you consider that the Earth is 4,000 miles to the center, it's really not down that far at all. Okay, 2 terms I'll talk about just because I might mention these as I talk about plate tectonics. Lithosphere. Lithos means rock. So this is the rocky, brittle, we'll come back to brittle here in a second, part of the Earth that includes not only the crust, but the upper part of the mantle. And what I mean by brittle is, if I take a rock and put it on this table up here and get a big old sledgehammer and whack the crap out of it, what's going to happen to that rock if I hit it hard enough? It's going to shatter and break, right? That's called brittle deformation. It's going to deform brittly. It's going to break. You understand that because if you've ever hit a rock with a hammer, rocks break. They shatter, right? So rocks will behave that way all the way down into the upper mantle. So this rock that we call the lithosphere is solid, brittle rock, just like what you're used to seeing, okay? But at some depth, because of the heat and pressure, rocks start behaving differently. That's called the asthenosphere. And instead of rocks behaving brittly, instead they behave like a plastic. If I have a big mound of putty up here, and I take my hammer and I whack it just as hard as in the previous example, what's going to happen to the putty? It's just going to kind of smush out, right? It's going to bend. So rocks in the lithosphere break brittly. Rocks in the asthenosphere flow plastically. They move. They're able to squish and move and deform. When we talk about plate tectonics, the plates are actually made of the crust and upper mantle, the lithosphere. They're technically called lithospheric plates. So this is the part of the Earth that breaks brittly and creates plates that move over the more deformable plastic mantle asthenosphere that lies beneath it. So brittle lithospheric plates, including the crust and upper mantle, moving on a mobile plastic deeper part of the mantle called the asthenosphere. Okay, so let's get into plate tectonics. We'll get into plate tectonics, we'll continue a bit into next class, and then we'll start with volcanoes, earthquakes, tsunamis, and all the other solid earth hazards that we have left to cover this semester. Like I said at the beginning of the class, though, this idea of plate tectonics is only about 100 years old. Okay, it's pretty recent, but as a theory, it allows us to make predictions of the Earth that we would have never been able to make before, and it allows us to understand hazards in a way that we would have never been able to before. So, kind of our timeline starts about 100 years ago, in the early 1900s, just before World War I. Okay? And this name, Alfred Wegener, he was a German climatologist. So he was kind of like Dr. Larrick. Okay? He studied the air, he studied climate. And he was really interested in past climates. What he found really interesting is that you can go to really cold places like Antarctica and find fossils that came from tropical climates. And he found that really fascinating. It's like, wow, how did that happen? How could Antarctica be so cold today, but at some point have had tropical type plant and animal growth there? So he was what we call a paleoclimatologist. He looked at older climates and how climates have changed on Earth. And he became really interested in fossils especially, because fossils told him about the climates of the past. But before Alfred Wegener came along, geologists had a view of the Earth that's really different than today. And it made perfect sense at the time. They basically thought that the Earth that you see today is the Earth that's pretty much always existed. The face of the Earth, the pattern of the continents that you see today, they believed were always there. North America was always where it was. Antarctica was always where it was. And that the face of the Earth really hadn't changed much through time. So in order to get tropical fossils in Antarctica at the South Pole, that means that thinking at that time was that, wow, the South Pole must have been really warm at one point. It must have been tropical. And that was kind of the accepted view, and nobody had really challenged it. But Alfred Wegener was into fossils, and he was into rocks, and he saw some evidence that painted a slightly different picture to him. And his ideas were extremely far out at the time. I mean, this idea that the Earth had always pretty much had the same face, that was really ingrained in science. Nobody would challenge it. But along comes this guy, he's a German around the time of World War I, and he's not even a geologist, he's a climatologist, and he's going to tell all these geologists that, you know what, you guys have been wrong. You guys have been wrong about this the whole time. His ideas weren't well accepted, one, because he was a German climatologist, and also because it was a very radical change in how we viewed the Earth. And he had a few problems with his ideas early on. So his ideas were really different. He said, rather than these tropical fossils in Antarctica forming because Antarctica was hot, what actually happened was Antarctica wasn't there when those fossils formed. Antarctica was in a more tropical part of the Earth, and it moved. The continents changed position over time. And that was something that up until that point, no one had proposed. He called it continental drift. His idea was that the continents sort of moved over the seafloor, changed their positions over time. And in fact, he said, you know, at one point in time, there weren't a whole bunch of continents, there was just one. He goes, I have evidence that shows that at one point we just had one continent, and he called it a supercontinent, Pangaea. Well, like my dad used to say, you know, this idea went over like a turd in a punch bowl. You know, it just, not something people were ready for, not something people wanted to deal with. His ideas were laughed at, he was ridiculed, he was mocked. The biggest problem Wegener had was that he couldn't explain how the continents moved. How do you get a continent the size of North America to slide over the ocean? What's forcing it to do that? And he couldn't explain it. He did not have a good idea for it. So there was some bias against him as a person, but he also had some holes in his story that really made it difficult to believe. But he had some really neat evidence. And that's what I'd like to show you for the next few minutes, is Wegener's evidence. How did he come up with this crazy idea that the oceans and the continents change positions over time? Well, one thing he noticed, and it's probably something that maybe even you've noticed by looking at a map of the Earth, is that our continents kind of look like puzzle pieces. And if you rearrange them, they all fit together pretty nicely, actually. I'll show you a diagram here. So you've probably noticed that especially South America and Africa, they fit together really well. And if you take not only the continent, but a part of the continent called the continental shelf, which is sort of this white area on this map. The continental shelf is sort of the shallow ocean area that exists off the continents. When sea level is low, they become exposed, and when sea level is high, like it is now, they get buried. But if you include the continental shelf, then they fit together super well. And he said, look at this, all these continents fit together pretty nicely. And even more than the continents fitting together nicely, there's some interesting patterns with glaciers. So we know we've had ice ages in the past where glaciers have moved on Earth. And one cool thing about glaciers, when they move across the Earth, they drag rocks and debris with them. And a lot of times those rocks will scratch rock that sits beneath the glacier. And you see these nice scour lines. So if you go up to an area where there's a glacier that was moving downhill, you'll see these lines that point in the direction it was moving. Because the glacier would pick up these rocks, just drag them, and they would dig into the rock below. So they're called glacial striations, and they indicate the direction of movement of the glacier. And you can even, if it's a line, you can even tell which direction just by feeling the roughness. One area is far rougher than the other, and it points in the direction that the glacier actually moved. Well, when he looked at glaciers from old areas, check out here in South America, okay? This area down here all has evidence that there were glaciers there during some older ice ages. And these arrows indicate the direction that the glaciers were moving. Look at South America, look at India, and look at the southern tip of Australia. What do you notice about the direction that ice is moving? Look at this. It looks like it's moving from the ocean onto the land, right? Shouldn't it be going the other way? Glaciers move downhill, right? This is moving uphill. Look at this. This is moving from the ocean onto land, from ocean onto land. That didn't make any sense until he put all the continents back together. And then saw that there was a big ice mass here, and the ice was flowing out in all different directions, making all these patterns that you see on the various continents. Geologists couldn't explain that, but Alfred Wegener could. So that was some good evidence that the status quo idea really wasn't very good. He also, like I said, was really into fossils. And he noticed some really neat things about fossils. And he was particularly interested in this fossil called Mesosaurus. Mesosaurus was this animal that could live mostly on land, probably in rivers, but it certainly didn't look like it could swim vast distances across the ocean. And yet you would find it here in South America, and you'd find it over in Africa, and you'd find it on some of these other continents. So it's more of a land-dwelling creature, but it was found on all these different continents that up until that point geologists had thought were always separate. Well, how did this thing move from one continent to the others if there were oceans in the way? And you could see that more with this tiger-like fossil that he found. Those things definitely aren't swimming across the oceans. Geologists would try to explain it by saying, oh, there were lots of islands out in the ocean that we don't see today, and they would swim from one island to the next, and I guess they would magically pop up and then they would magically disappear after the animal made its migration. But Wegener said, this is a much simpler explanation. All these continents were together, and these animals could just easily move from one landmass to the next. So again, something that Wegener could explain that geologists couldn't. And he also found that there were some interesting similarities in rock types between continents. If you go to the east coast of the US and look at the rocks there, they are identical. I mean, absolutely 100% identical in type, in age, in the way they're deformed, as rocks that you see in the northwest corner of Africa. It's like, well, how are you getting the exact same rocks forming thousands of miles apart? I mean, what's going on? How does this rock know to be this rock, and vice versa? And he said it didn't. At one point, these were together. They were one rock unit. Then these continents broke apart, and these rocks rafted to different parts of the world. So that was Wegener's evidence, and it's pretty compelling. But geologists said, okay, cool story. How on earth does a continent move across an ocean floor? And he couldn't really answer it. He did not have a good explanation for how these continents would move. He tried a really poor explanation. He said, well, the Earth's spin is making these continents move over the floor, but you can do simple calculations and find out that the spin just isn't fast enough to move something as massive as a continent. So at the end of the day, he couldn't explain how it worked. And his ideas were just tossed aside in the early 1900s. Alfred Wegener actually died before his ideas came back into the scientific world in a positive way in the 1950s. So sadly, he died kind of an outcast, but basically he was right. He just didn't understand how it worked because he didn't have all the information. And the information he didn't have was from the bottom of the ocean. In the 1950s, the US, Europe, the Russians, all started studying the seafloor in great detail, mostly because of World War II. They wanted high precision maps so that subs could move more effectively during wartime. So we spent gazillions of bucks mapping the seafloor. And it was mapping of the seafloor that resurrected a lot of Alfred Wegener's ideas back in the 1950s. So we will get into that next class and finish it up. And I don't know whether to talk about volcanoes or earthquakes. I still have to decide. So if you guys have any questions, I'll stick around. If not, I'll see you all on Thursday.